talking about databases and my deep, unabiding love of them. At least you guys will know where I stand, right? I love all sorts of databases. I like distributed databases. I like, individual databases. I like column store. I like row store. I can't express enough of how cool I think databases are because they enable me to run analysis that I can't do any other way. All right, so there's a reason I love them. I think that you should love them too. I want to quickly ask you guys a few questions to get, to figure out how much you love databases. Can we just kind of quickly see a show of hands? How many of you guys have heard of Hadoop before? Okay, great, awesome. Now, how many of you personally, not someone that works for you, have used Hadoop?
Knowingly or not knowingly?
What? So about 6 of you have used Hadoop before. How many of you have heard of Spark? Okay, how many have used Spark? Okay, awesome. All right, so, and now one last question. How many of you consider yourself simulators? Okay, and how many of you simulators have used databases before? Okay, all right, so I'm hoping by the end of this to convert you guys, to preach the gospel and get you guys to drink the Kool-Aid of databases and how they can be applicable to you. A few of you I already have on my side. I'm hoping to gain more of you by the end of this conversation. And I'm really going to emphasize a series of 3 papers that my collaborators and I worked together on. By collaborators, I mean both the simulation group that I work with, the N-Body Shop out of the University of Washington, but more significantly, the UW Computer Science and Engineering Database Group. And there's a long list of people up here. These people have made my life much, much better. I'm going to mention this again, but when we get to the video that you guys won't be able to hear anyway, it will be the voice of Jennifer Ortiz. You want to hire her. She's getting a data science PhD. She's a computer science student. She's close to graduating. She is amazing. So, if you can convince her to work for you, you should look her up and try to convince her to come your way. But, she has Google and everyone else trying to hire her. So throw lots of money her direction. All right, so the problem. I wear both an observer hat and a simulation hat. I'm really interested in the formation and evolution of Milky Way-like galaxies, structures therein. But today, probably much to Shelpa's chagrin, I'm taking the observer hat off, and I'm only wearing the simulator hat. The reason I'm doing this is because the simulations we work with, obviously the observations we work with are incredible, but the simulations that I'm going to discuss are really state-of-the-art, not just in astronomy, but in the science community as a whole. Okay, and in the recent past, our access to computational resources has made it such that we no longer have our data starved on the simulation side, but we have a huge amount of simulation data available. So I'm going to be talking about terabytes of particle data, but this is just a starting point. Blue Waters has already come up in conversation today. We're starting to generate exabytes of simulation data of small individual groups. So as opposed to a large collaboration, we're talking, 10 people with access to exabytes of data. The problem with this, it's an embarrassment of riches, but we're really suffering a bottleneck at this point because we can't actually run our analysis code on it anymore. All right, so we have to reframe and rethink how we approach science because we just can't use the old techniques that we in the simulation community have used in the past to effectively do the science that we want to do on these new data sets. This was the motivation, or this new needs for applying new analysis tools or techniques is really what motivated the collaboration that we developed between astronomy and computer science. I spent a large amount of time in my early grad career sitting in front of computers waiting for data to load. This was not the best use of my time. I mean, I did work on the side too, right? But I did spend a lot of time just watching the data load, and it seemed like my time could be spent more effectively. The database community is a huge collection of people worldwide that have developed these really robust and commercially available platforms that load in your data and make your data available in such a way that you never need to wait for that load time to happen. Right? So there's a group of people that have already thought about how to store and make your data available quickly. Just for some perspective, right, there are roughly 10,000 astronomers worldwide. There's at least an order of magnitude more people involved in the database community worldwide. Okay, so, and these people are highly motivated to do a good job developing these databases because they're developed originally for use in the financial market. That is, they have lots of money backing them. They want to track transactions really well, financial transactions really well. Okay, so there are these robust and commercially available database products. We know they work well, but they haven't really, until very recently, been tested as a means for conducting analysis for scientific data sets. I mean, really only in the last 5 years have we started to think about this. Is this possible? Now, we all know from Sloan and other projects that the databases have been used for serving the data, just whether or not they've been used for analyzing the data. This is a new issue. Okay, so these tools may be useful in the scientific community. But when we started thinking about this, we actually really hadn't found any sort of benchmarks that have been done to say, well, is it useful for us? Is it useful spending the time figuring out how to get our data into the database and use it in this way? So we set out with the goal to conduct a bunch of different benchmarks, just to figure out, is it useful to invest our time as scientists using databases as a primary source of analysis? The data sets that I am using, I'm going to discuss, come out of the N-body shop. They are generated using gasoline. Gasoline is an N-body plus smooth particle hydrodynamic code that's been in development for roughly the last 20 years. When you guys all know George Lake, he was here, he has now left. He is the godfather of the N-body group. He helped develop this code. He's been on the forefront of developing these big data sets. The data sets that I'll be discussing are on order. The last one that I'll discuss at the end of my talk, 10 to the 10 particles in it. The way it works is you take, for cosmological volume, you take the 10 to the 10 particles and you spread it out across a box, given an initial power spectrum, and then you just let time move forward and gravity work, right? So not only do we have gravity working in these simulations, we also have hydrodynamic processes occurring, but the main thing you can think about is the formation of structures being driven by Newton's equations, right? These codes take months to run. And the first data set I'm going to discuss, it took 7.5 million CPU hours to generate. The end output from that is roughly 500 snapshots of the simulation. Now, what do I mean by snapshot? We've actually seen this slide a few times already in the course of this conference. The way it works, in an ideal world, we'd know where every particle was at every moment in time. But I think that there's a disconnect between simulators and observers with understanding that we know a lot in our simulations, but we actually don't have the means, we don't have the disk space nor the time to write out every moment in the simulation's history. So as a consequence, we only write out data to disk, the positions of particles and a slew of other properties at discrete moments in time. Right? So this makes us a little bit more like observers than most of you are used to thinking of us as. We don't know a priori the connections between all the particles at every moment. You have to actually figure out where particles move between the different time steps, right? So a snapshot, when I refer to snapshot, it's just the state of the system at a discrete moment in time. And this picture involves the vast majority of what I've thought about lately. How do I track these 10 to the 10 particles between each time step? How do I take 10 to the 10, all the properties of those particles at a individual moment, and then across 500 moments in time. Okay, so what is the simulation data? Why is it beautifully tuned to fit very well in the database framework? Well, of these interdependent particles, we have three types of particles. We have gas particles, star particles, and dark matter particles. And these particles adhere to a very rigid structure of properties that we track. They all have unique identifiers associated with them. They all have positional information associated with them, and a slew of other things. In addition to that, when the simulation starts, we only have gas and dark matter in it. As time goes on, as the universe evolves, then stars are able to form. So you can think, there are some properties that are universal between all these data, all these particles, and then there are some properties that are unique to the particle type. All right, so this means that when we think about storing our data in a database, there are different ways we could arrange it. We could do different schemas. The way we've default done everything is to load all the data, each snapshot at a time. So a table per snapshot, recording all of these individual properties and then joining it with individual properties for things like stars. The really, really important point to remember is that we have both spatial and temporal information. So as we store our data, we have it in separate tables for each moment in time, but we're going to have to figure out how to connect those moments in time together. All right, so what are the current analysis techniques? What do we do in the n-body shop when we don't use the database? There are really two flavors of what people have done in the past. People write handwritten C code, and this can be wicked fast and work really, really well. Unfortunately, it's time-consuming to develop these application-specific libraries, and they really kind of live and die with particular people, right? The other thing we can do is write scripts and interpret them. This is more and more what we are doing. The problem with this is that these interpreted languages, they typically operate in main memory, so you become memory limited, right? And so here's, okay, and before everyone starts groaning because the word IDL is on the screen, I want you all to know that the legacy code that was developed in the group was all in IDL. So we ran these tests in IDL. In the time since we ran these initial tests, we've also developed code in Python. We've looked at these tests for Python as well. The same bottlenecks, the same timing apply. Maybe slightly faster in Python, but the principles I'm showing you here, you can substitute the word IDL for the word Python, and the same principles hold, okay? So, no killing me at the word IDL, all right? The way IDL works is that you load one snapshot in at a time. And you're limited by mean memory. Temporal correlations rely on the availability of memory. That is, in the past, if we wanted to track all the particles in the simulation, you could at most load 2 snapshots in at a time. Maybe 3 if you had a very large memory machine. And as Mario pointed out, not only are we suffering from having large size of data sets, but the I/O bandwidth of systems is encroaching really slowly. That is, even if you have memory available to read these snapshots in, it can take a really long time to read it from disk into your system. Okay, so if I start up IDL at the beginning of each day, that what I was suffering was waiting an hour to load one snapshot in. That's a horrible waste of time, right? And you have to do that every time you run this any sort of analysis, right? We don't want to be limited by having to wait to load in the data. All right, so what our analysis needs, we have figured out that there are kind of 3 categories of analysis that we have typically operated on or wanted to do. One is filtering and correlating properties of particles. That is, selecting interesting particles, whether it be by their spatial location or given a particular property like temperature. Right? Additionally, we were interested in clustering the data. Now you can think of it in terms of clustering it in space and identifying a collection of particles as a galaxy, or you could think of it as looking at some different cluster in a different parameter space, right? Once we have identified what galaxies are inside the simulation, we'd also like to be able to track these galaxies and how these galaxies build up over time. That is, we'd like to run queries on top of the clustered information and correlate it between right? And look for correlations and interesting interesting properties in that parameter space. Okay, so we wrote 3 papers revolving around these 3 different workloads. And the one thing that you should ask yourself, and I ask myself all the time, is it easy to express these analysis needs in the method that we're trying to do in the database? And is it fast to run? Those are the 2 things we really care about. For the first paper, just, is this worthwhile to do? We developed 5 benchmarks. Now, by the end of today, I know many of you have heard of Hadoop before. As you walk out today, you should hopefully know how Hadoop works. Okay? And based on what I'm going to tell you about how we've constructed our queries here. Right? So we ran tests IDL on a relational database management system. The one we used was MySQL server. Microsoft SQL server. And then we also ran these tests on Hadoop. All right? And the types of benchmarks we developed ran on things that you've all thought about in the past. When you go to Sloan and you run a query, a select query, we've looked to see how easy, how quickly these select queries work on our simulation data. And we also looked at joining, so joining these tables together, right? And I'm going to show you an example of both. And I'm going to show you the time it took for all of these systems. And I want you, when you walk out, I want you to have a sense of which worked best. Is it Hadoop that works best? Is it Microsoft SQL Server? And what should you do with this information when you go home? All right, so how does a relational database management system work? How does Microsoft SQL Server work? The idea is that you use a declarative language. You use SQL. I don't know how many of you guys know this, but SQL, relational algebra, is a Turing-complete language, meaning in principle, you can express any scientific question you want in SQL. Whether that's worthwhile to spend the time to construct it in SQL is another issue, but in principle, you could express any question about that. All right? And what does Microsoft SQL Server do? Well, you just tell the database, I want this information. I'm not going to tell you how to get that information. Select the particles given this attribute. And this is actually a query, very straightforward to run. Select gas with this property where it's above a certain temperature. You send that select statement to the database, and the database is a query processor that optimizes it, looks at all the different ways to run that query, and picks the fastest query plan, and then gives back you the data. So this is a declarative language. It leverages indexes, so it runs pretty quickly, and it skims over irrelevant data. Ooh. Okay. Here's an example of the 2 types of queries we ran with a select statement and a join. What I want you to see is these sorts of queries are very easy to express. It takes no effort at all. So what is Hadoop? Hadoop is an open source version of MapReduce. That is, it's a powerful platform that runs on shared nothing architecture. You can take as many computers as you want and stitch them together. They don't need to know anything about each other, and you can make it into a database. There's no predefined schema. You don't have to, in advance, tell it the structure of the data that you need. But then there are also no indexes. What is Pig? It is not actually Pig. It is Pig Latin. It is the language that runs on top of Hadoop. And it is a wrapper that is very similar to SQL. In fact, I'm not going to show you any Pig Latin statements because they're close enough that you can, in your mind, substitute one for another. So how does Hadoop, or MapReduce, work? Okay, I'm going to give you an example. And it's an example that is motivated by my children. It has to do with candy and Halloween. All right. Halloween, the kids go out, they go asking for candy as they go from neighbor to neighbor. They collect all sorts of candy. And then what do they do when they come home? They sit down and they sort their candy, each kid by themselves. I don't know if you guys had this experience of doing it where you're like, the thrill of all the candy I've got. I'm going to sort it into different piles. All right. This sorting of candy by individual children, you can think of it like individual computers, individual nodes. This is the mapping part of the MapReduce paradigm. What you do is you just sort the data according to some particular property. The second part of how any sort of query gets executed inside of Hadoop is reducing. This is the part that is contentious with children. You don't want to swap around to figure out how many overall I don't know, M&Ms we have, you'd rather keep your data to yourself. It takes some negotiation, it takes some time to do, but if you can work as a collective and swap your data around, you can rearrange your data so that you have your data collected by type. And then you can sum up, say how many fizzers I have, how many Twix I have, how many jelly beans I have. So as opposed to considering per kid, now we're looking at the global system and per type of information. Okay, this is how it works. This example, however, and reduce tends to be where the bottleneck is. All right, so when you actually go and run MapReduce, you almost always have problems, or it runs longer on the reduce side of things. When you're swapping the data around, reshuffling the data to then do an aggregate account or whatever collating of the information you want. And so just like what we're talking about in SQL Server and Hadoop, in principle, you can express any question you want that way. Whether you write it natively in Java, which is what Hadoop uses, or in Pig Latin on top of it. So the two types of queries that we ran, one involved only using the macrophase. So it was pretty fast. And that was the simple select statement. What we did was we chunked our data out to all sorts of nodes, and then we selected, it sorted the IDs, were sorted by temperature on each node, and then we just returned the relevant IDs that matched to proper temperature. Okay. The harder task, or the more time-intensive task, was running a hash join. The way it works in Hadoop is that each node gets two chunks of data that you're going to join together. When you get these two chunks, you then you sort that data, and you make a hash partition, and then when you shuffle things around, you shuffle so all the IDs get collected on a particular node, and you say, when in the case of a join, you make sure that the cases where the two IDs match, versus like where a gas particle is deleted, the case where it exists in one time step and is null in another time step. And that returns back, in the case of the fourth query that we ran, the result that we were looking for. This takes longer than just mapping. So we ran our initial queries on 3 different data sets, and when you look at this, you might think, oh, well, these aren't actually very big data sets. They're pretty big in the native binary format, the TIPSY format that we use on the simulation side. But I really wanted to show you this data set, this expression, because SQL Server compresses the data down in a wicked way. Right? So it was actually, the data was order of magnitude larger per snapshot originally. But when we ingested it within the database, it was optimized to compress the data in such a way that it got much, much smaller. So we ran these queries on 3 different data sets. And what I'm going to show you now for these 5 benchmark queries is how long it took to run them. All I want you to take away from here is something that you think would be stupid fast to run. Like if you go to Sloan to run, a simple select statement on these data sets actually took a pretty long time. The largest data set that we used, which had 768 cubed particles associated with it, when we just grabbed particles based on their temperature, well, IDL always took the longest, on order 1,000 seconds. Okay? But it actually, for a single node, if you're only executing the job on one node, it took a pretty long time on Hadoop. And a similarly long time, a database C here is Microsoft SQL Server. The thing, yes?
Just a question, but does that time take it to...
load time for IDL. Because you have to do that every time, we felt that it was fair to include it as a part of the runtime. It is fair for a debate. We thought about it pretty.
Gets amortized over time, right? If you have multiple queries.
Yes, for sure.
Sorry, can I just ask? These are all running on equivalent hardware systems?
They are.
Okay.
So what do we do next? Well, we took Microsoft SQL Server has the option to stitch together multiple nodes to make it a somewhat distributed system. So what we did, we could only do this up to 8 nodes. But we ran a comparison between adding more and more nodes in Hadoop versus how it works on Microsoft SQL Server. Because Hadoop is really, really cheap. It's actually free. software that anyone can download, and it's pretty cheap to get Microsoft cluster going. But Microsoft SQL Server is pretty expensive. So you want to know, is it worthwhile to spend time using Hadoop? But what we found, up to 8 nodes, yes, in the beginning, Hadoop doesn't do very well. But as you throw more and more and more Microsoft cluster nodes in there, the times start to come together. And Hadoop continues to go down. It scales very, very nicely as you throw more nodes at it. So our takeaway here, yes, in this limit, in the 8-node limit, Microsoft SQL Server always won in terms of it took less time to run these queries. However, Hadoop had significant gains, right, over as you added more nodes on. Interesting thing was query number 2. This is not actually the case. And this is because we indexed in Microsoft SQL Server. You can't index in Hadoop. But in the case of query 2, we couldn't index. And you can see the value of indexing because here, once we got up to 2 nodes without any index, actually Microsoft SQL Server lost. It took longer. All right, so the join type of queries. How long did it take? Right, so now we're getting up in the hours range time that it takes to run things. Just joining between 2 snapshots, not 500 snapshots. Right? For a single node, in this case, okay, again, database always won, but actually for a single node, Hadoop lost. But when we scale up, once again, we see the same pattern of Hadoop getting better and better and better as we get to more nodes. What was our takeaway here? What was the lesson I learned? I found actually Pig and SQL really easy to express the questions that I wanted to express. Okay, fair. Small sphere clusters, we found that Microsoft SQL Server is always the better way to go. However, Hadoop speeds up more consistently. And no matter what, Hadoop and relational database management system always outperformed IDL. And you can substitute the word Python there, too. All right, so where do we go from there? Well, we want to identify clusters of particles. And I'm going to speed up a little bit, try to go a little faster, and just show you tastes of the other 2 things that we've explored. Okay, so when you run a simulation, it's just particles. There's nothing that says, this over here, this is a galaxy. You actually have to, after you run the simulation, run a post-processing algorithm on top of it to identify what collection of particles should be considered a galaxy. This is called a halo finding algorithm. We decided to make a halo finding algorithm inside of the database and minimize running external code. The one we decided to implement is actually the easiest one to implement. It's called friends of friends. And the basic principle works like this. So you have 2 particles, particle A and B. They are friends of one another. They're considered part of a bunch. They run together in a pack when they're within a certain distance, less than this epsilon. Now, you can imagine particle C and particle B, they're also friends. They're within that length. So what is a friend of a friend? Well, C is a friend of A. A friend of a friend of A. That is, they both have a friend in common, B. We run these algorithms to see what particles are associated with one another through this chain of friends. So what we decided to do was make a distributed friend of friends and run it in Hadoop. And also dry inference. How does this work? Well, you spread your data across a whole bunch of different nodes. And then you map. You do your first step. You look for your collections of particles. In this case, on the first node, you can see there are 3 different collections of particles. Now, on the other nodes, we only have 1 collection in each place. But now, if you defocus your eyes a little bit, you see that these are actually not 4 different clusters. They're actually all connected together in one big structure. This is what's challenging about friends of friends in a distributed framework. You actually have to go a step further and figure out how to communicate this interconnectedness between the different clusters of data. So what is the solution that we came up with? The solution that other people have thought of too, but that we implemented within the database framework. Well, what we did, going back here, we made a little border. And we said any particles that are on the edge, those particles we're going to allow to swap around to consider how across these nodes they're connected. All right? And we did this in 2 steps. First, we looked across this partition. Then we swapped and we said, oh, okay, look, these guys are connected together, and these two are connected together. But then we needed to do it again. Whoops. So that we could then see that this is connected together. So you can see there's this iterative action to it. It ended up taking 66 lines of code to express an entire friend-to-friends algorithm. It is a lot less than how expressed in any other friend-to-friend finding algorithm. It worked. The lessons we took away was most of the time was actually spent on local clustering per node, that mapping phase. You can do some clever things with load balancing to make it go as optimal as possible. There's a range of runtimes and memory utilization depending on how the data was distributed, how you're dividing what you're considering per node. We found some really cute ways to speed it up by pruning trees and how we made partitions. It was highly scalable and near linear speed up and scale up. So it was great. I don't actually, if I want to trust friends and friends, I never actually have to run this Halo finding algorithm separate. I can always have my database do it. And do it pretty quickly if I throw a ton of nodes at it. There we go. All right, so the very last thing, before we're all free to do other things, tracing galaxies over time. This is really the end goal of where I'm trying to get. I want to understand how galaxies build up in these simulations. So anecdotally, what we found was that there was tons of interest in what we were doing with the database, but no one wanted to learn how to use SQL. No one wanted to actually do the They had enough things on their plate. All they wanted was for me to show a nice, neat end product, right? So this became both a benchmarking in terms of how can we make things run very quickly, connecting between time steps, and get people within my community of simulation people to want to use it. And the solution we came up with is My Merger Tree. It's a cloud service for creating and analyzing galactic merger trees. Very quickly what this is, a merger tree is just a way of thinking about how galaxies build up over time. That is, if you have a galaxy that we've identified with our Halo finding algorithm, we can say, this cool galaxy, I want to know what it was like a giga-year ago. Well, you can look and see, was it just one galaxy, a time step before? Or maybe it was two different galaxies that merged together. You can trace your particles back in time, see what halos they're associated with, to figure out how a galaxy builds up, and create a visualization like this, which shows you what particular halos merge together. You can imagine this not just in spatial space, but you could think of it clustering of other properties across time as well. We wanted to think about what tools can generate this sort of structure of data. What we ended up going to was developing a new type of database. It's called Miriam. It's much like Spark. I actually think it has some great advantages over Spark. It's fabulous. The way it works, we wanted something, a data service that can match billions of particles across time. It also had to visualize fast, be platform independent, and easy to use and share. All right, so we needed a data service, and we needed a cloud service to make it easy to use and share. And what we came up with was this. It's a in the cloud RESTful query as you go service platform. It's expressive. That means it's a compiler framework for a whole bunch of different relational algebra based languages. You can also give your workload in Python if you want. All right? It's efficient. It's parallel nothing architecture underneath it, and if you care what actual particular databases on each node is, a Postgres that's been effectively tied together. This is what it looks like. Just so you know, you can enter your query in. This is what runs in the browser, and you can select what language, or if you want to give it your own script. You can also see how the query runs and get the results back out. All right.
I think that we would like merge tree visualization and how it works with the Miriam database system backend. So in this tool, I can select the Miriam merger tree gadget, select Start Dashboard, and this will take me to this interface where I can simply type in my username, and also select the mass region I'm interested in. And these mass ranges can range from dwarf galaxies up to Milky Way, for example. So this example is like Milky Way range, and then click on Generate Groups. And what this does is it sends a query to the Myriad backend system, which selects those groups that fit the mass range that I selected. And then from there, I can select the group that I'm interested in. So here, I select this halo. And what it does is it ships this group information to Myriad, which then provides the merger tree result. So here, we can zoom in and out of the visualization. We can hover over any of these nodes to find more information about the number of particles, the mass of the halo, etc. We can also click on some of these paths to collapse them. At the bottom, we can select different halos based on different properties. For example, we can select based on mass ranges, so we can use this brush tool over the graph to select different galaxies that we're interested in. And once we've highlighted them, we can download more information about them using this download button up here. And what this does, it brings up two tables. One shows the galaxies that fit that the highlighting that I've done using the graph. The other one represents the connecting edges between each of these halos. We can also select different mass range ratio. For example, here we set it up to 5. We can do it to find more or larger mass ratios. And once we update, we can see that there's different halos that were highlighted yellow to show the major mergers. So what this does is we can take a closer look at the Myriad service and see what that's doing. So as we were doing this visualization, you can see that we ran these queries here. So here Myriad was able to run these queries, and the visualization was able to get these results, the edges and nodes results, to build the tree. And we can also build our own custom queries. So for example, here in the editor, we can create our own query, only obtaining information that we're particularly interested in based on some galaxies. So for example, here I'm querying the halo table. I can select the specific group ID that I'm interested in and also download that result. So here we can execute this query. And this will run in the system, and then we can download the result JSON, CSV, or TSV format. So here, for example, you can see more information about that particular galaxy that we selected. And we could also not only use the editor, we can also use Python as well. So here's an example of a Python tool that we can use to connect to Myriad, and then we can describe the query that we want to run, and then finally execute that query on the system, which will also run on our Myriad service.
Okay, so you didn't actually know I had to know ODPs, and we didn't actually have to know any SQL in order to generate a merger tree, to get the results out, to do any sort of exploratory science on this huge data set that had thousands of galaxies inside of it, right? This is the first time that I got anyone in my group, astronomy side group that I work with, have any interest in this, right? So making it easy for data exploration. So where we went. Now there are 3 challenges we thought at the outset that we would run into. How to express this problem declaratively, how to tune it for high performance, and how to visualize it naturally and easily. We thought these were the problems, only one of these actually was a problem. Great, so I'm going to skip over this, but if you guys want to talk to me later and hear how we actually do this, this is all based on tracking those individual particles over time. And it really involves just selecting and joining. It was remarkably easy to express. We thought it was going to be really hard, but it turned out it was trivial to express the query. Now, how the data was arranged turned out to have a huge impact. So these were some initial results. We actually found incredible speed up since then. But what I wanted to show you is if you think about how you want the data arranged on disk before you distribute the data to all the nodes, it makes a radical difference in how long it takes to actually run the queries. This is the moment when having an astronomer that has some knowledge of the sorts of queries we want to run, interfacing with the expert of distributing the data, the database person, really, really matters. You want to be able to say, this is what I care tracing. In this particular instance, we learned that if you distribute things according to those particle IDs, instead of doing a round robin for the data, or instead of distributing it according to space, that makes a huge difference in how quickly things go. Hashing on ingestion matters. So this was the obstacle, how data was arranged. And mattered for the question that we wanted to ask of the data and how quickly we could get the answer back. So the last kind of point, we thought that it would be hard to visualize this stuff. It turns out D3, I don't know how many, probably many of you guys use D3, but D3 was fabulous. It's so easy to use for visualizing. I can't stress enough what a great thing it is to take D3 and connect it to your database, to have some way to visualize your data very, very easily in JSON format. So here's some of my last kind of conclusions of this part of it. The translation of our problem was easier than we predicted. The fine-tuning is what required the most effort. Specialized visualization tools exist for anything you want to visualize. And ingesting and validation is something we're still working on, thinking about. So now we're at this point where we've actually addressed all the 3 different types of workloads we wanted to address. Now we want to ask, how can we additionally solve other problems? More than that, we want to think about how can we speed up our data exploration. What can we do to maybe not have something run over all the particles, but self-select the particles? We'll get an approximate answer so that we can see if it's worthwhile investing all the time. So this is where I'm hoping to explore other database sort of platforms like BlinkDB. I should say that's something else I'm really interested in. What lots of database platforms have started to, or Spark in particular has started to do, is integrate machine learning analytics inside databases. Support vector machines, naive Bayes, all this sort of stuff is being integrated inside the database. That is, the sorts of stuff that many of you in this room are interested in is now possible to execute inside databases. I'm hoping this is whetting your appetite. You now know someone who loves databases. Come talk to me if you want to think more about if it's worthwhile to take your analytics and think about applying it inside of the database framework. And remember, databases scale, right? And so your techniques, how you apply it right now, maybe don't. They possibly do. But this is a great way moving forward as we move towards LSST-sized data sets. This is a great way to be able to continue to do our science and the analytics. One other thing I'd like to mention, back to that issue of how data was arranged really mattered. One of the things I'm hoping to work on over the next year is exploring how dynamic arrangement of data might impact how quickly we can return results.